Hi everyone. In this video we're going to go over Skill Builder Exercise 3 in the IR and MS chapter. So if you have the third edition of the textbook, this will be number 14.3. In the second edition it's 15.3. So here I have the second edition version. But in this problem, we're going to use the relative abundance of the m+1 peak to propose a molecular formula. So last time we saw how to determine the number of carbon atoms in your compound using the relative abundance of the parent peak and then the m+1 peak. So we're going to use that. We'll also use a couple of other tools in our toolbox to try to figure out the molecular formula. All right, so on the left we have the mass spectrum with relative abundance versus m/z. And we also have a table with the mass spectrum data. So this is giving us the m/z values that are found on the mass spectrum, as well as the relative height of each peak, so their relative abundance. Okay, now the first thing I'm actually going to do is identify the parent peak. So remember, to find the parent peak, you want to go to the furthest cluster on the right. So that is this cluster here. And then you want to find the tallest peak, which is this one. So it looks like that's at 86. And if we look at our chart, the parent peak is also labeled at 86. So that tells us that the mass of our compound is 86 grams per mole. Okay. So remember, last time we talked about the nitrogen rule. So first, I'm just going to use the nitrogen rule. And remember, this rule said that if you have an even mass, then you either have just carbons and hydrogens, so a hydrocarbon, or you have an even number of nitrogens present. If the mass is an odd number, then you have an odd number of nitrogens. So here, 86 is our mass, and that is an even number. So that means we either have a hydrocarbon or an even number of nitrogens. Okay, so that's just something to keep in mind going forward. Second, I'm going to use our equation for calculating the number of carbons in our compound. So remember, last time we saw that the number of carbons is equal to the intensity of the m+1 peak divided by the intensity of the parent peak. And then we divide that all by 1.1 because that's the relative abundance of carbon 13 compared to carbon 12. And then we multiply by 100. All right, so let's plug in our values, and thankfully we were given those values in our table. So the intensity of the m+1 peak is 1.2. And then the intensity of our parent peak is 20.9. And I'm just leaving out the percentage sign there. So we'll divide 1.2 by 20.9, and then divide that whole thing by 1.1 and multiply by 100. Okay, so if you want to plug that into your calculator and see how many carbons we have, feel free to pause the video, and when you unpause, we'll go over the answer together. Okay, so I got about 5 as my answer. So that tells me I have 5 carbons in my molecule. Okay, so we figured out part of our molecular formula. We have 5 carbons. Now, in the next step, what we're going to do is determine our leftover mass. Okay, so we said that we had a compound with a mass of 86. So that's our parent peak. And now we're going to subtract the mass of those 5 carbons that we know are in the compound. Okay, so let's just do some quick math. We have 5 carbons, and each one weighs 12.01 grams per mole. So what does that give us? About 60 grams per mole. So I'm just going to subtract 60 from 86, and again, that's from our 5 carbons. And then I'm just going to erase the math down here to leave some room. So now this will give us our leftover mass, so the difference between these two numbers. So let's see, 86 minus 60, that should give us 26 grams per mole. Okay, so now that's the mass we have to work with to figure out what other atoms we have in our molecular formula. So earlier in step 1, we said that according to the nitrogen rule, we either have a hydrocarbon or an even number of nitrogens. Okay, so let's see if it's possible to have 2 nitrogens in our molecule, because 2 would be the lowest even number of nitrogens that we could have. Well, we'll write here maybe 2 nitrogens are in the molecule. But how much do 2 nitrogens weigh? So 1 nitrogen has a mass of 14, so 2 nitrogens would have a mass of 28 grams per mole. And that's greater than 26, which is our leftover mass. So we do not have any hydrogen or nitrogens in our compound, so we'll rule out nitrogen. So we maybe just have, let's see, we could also have an oxygen potentially. And we could potentially also have hydrogens. So, okay, so far we have 5 carbons. What if the rest of the leftover mass is just due to hydrogens? Well, each hydrogen has a mass of about 1, so that would mean we would have 26 hydrogens. Does that make sense? No, because our formula for a molecule is CN, and then we have our hydrogens, and the most you can have is, let's see, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So N plus 2. So if we have 5 carbons, the most hydrogens we could have is, let's see, 12. So 26 is way bigger than 12, so that doesn't make sense. So maybe we have an oxygen in our molecular formula as well. Okay, so let's do the math and see if oxygen makes sense. So step 4, determine the atoms in the leftover mass. So we kind of determined already that we might have an oxygen, which would account for quite a bit of the leftover mass. So again, we had a mass of 86 to start, and that was from our parent peak. And then we subtracted 60 due to those 5 carbons that we calculated. And now let's subtract 16 for the oxygen atom that we're assuming is in our molecule. Okay, so we said 86 minus 60 is 26, and then 26 minus 16 would give us 10 grams per mole. Okay, that kind of makes sense because maybe we have 10 hydrogens. All right, so we could write our molecular formula as C5H10O. And that makes sense. To have 10 hydrogens works with what we talked about earlier. All right, so we figured out the molecular formula, but there's one more thing that I wanted to teach you. And that's something called the hydrogen deficiency index. So let's say that in addition to figuring out the molecular formula, you wanted to also figure out if you had any double bonds or a ring in your molecule. So in this extra step here, we could calculate what's called the hydrogen deficiency index, or HDI, and this is similar to the degree of unsaturation in your molecule. So is your molecule missing hydrogens because it has a pi bond or a ring structure? So we can figure it out by doing this calculation. So the equation for the hydrogen deficiency index is equal to 1/2 times 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens. So you would have to know how many nitrogens, hydrogens, and halogens you have, which means you have to know the molecular formula before you use this hydrogen deficiency index. And again, this will tell us the number of pi bonds plus the number of rings in your system. Okay, so let's calculate this for our molecular formula, C5H10O. All right, so we're just going to plug in the number of carbons, which is 5. Then we're going to add 2. We'll add the number of nitrogens, which is 0 for our particular molecule. And then we'll subtract 10 for the hydrogens. And then we'll subtract 0 for the halogens. And notice that oxygen is not in this equation, so we don't have to worry about the number of oxygens. Okay, so let's see. 2 times 5 is 10, plus 2 is 12, minus 10 is 2, and then we'll divide that by 2, which gives us 1. All right, so that tells us we either have 1 pi bond or 1 ring in our system, and we're not really sure which one we have. Now let's say that this number was 2. So if a molecule had a hydrogen deficiency index of 2, that could mean we either have 2 pi bonds in the molecule, 2 rings in the molecule, or 1 pi bond and 1 ring. So you could have a mixture of pi bonds and rings, potentially. But here our value is 1, so we either have a pi bond or we have a ring. So let's draw some possible structures for our molecule. And these will all be constitutional isomers. So we're not going to worry about enantiomers. Okay, well, if we had a ring in our molecule, we might have something like this. We have 5 carbons, 1 oxygen, and if you count the hydrogens, we should have 10 around the ring. Maybe we just have a 5-membered or a 5-carbon chain with a ketone. Maybe the ketone is on the second carbon. Maybe we actually have an aldehyde. We could also have potentially an enol, so an alcohol near a double bond. Or I guess that's not an enol if the double bond's over 1. But you get the idea. There's lots of different options here. So unfortunately, with mass spectrometry alone, it is hard to piece together what you have. We would need a few more tools in our toolbox, or we could also supplement our analysis with something like IR spectroscopy. All right, so we'll stop there today, but the 5 steps that I took you through in this video are the 5 steps that you can use to try to figure out what your molecular formula is, and then start to get an idea of what the structure of your molecule looks like. So in the next video, we'll add a few more tools into our toolbox, and then we'll try to kind of practice figuring out what type of molecule we have.